Okay, hi everyone. Can you hear me? Yeah, okay. Thanks for joining today. I am Tamás Bám. I work for the open source software group within ARM. In the recent years, I have been working on a secure boot, measured boot, and attestation solution across multiple software projects under the trusted firmware umbrella. I have been contributed to MCU boot, TFA, and TFM. Today I would like to give you about an overview about a new attestation solution, which is the DICE and the EP. I would like to present you the work that we have done in the firmware space and explain how can it be used to enhance trust in the Android ecosystem. Okay, so first of all, what is DICE and DPE? DICE stands for Device Identifier Compound Engine, and DPE stands for DICE Protection Environment. Both are meant to create an attestation report in a secure manner. An attestation report contains information about the hardware and the software stack which is running on it. The objective of an attestation report to prove the trustworthiness of a device towards a remote party. These information which is included in the report usually collected at the boot time. For example, the hardware identity, the security state of the device, and the measurements of the software components. Measurement means in this context is basically the hash value of the image which was loaded to the memory. The attestation report is signed by the device, which is a key, a private key, and it can be retrieved anytime from the device and validated by the remote entity. The remote entity is aware of the corresponding public key, and it will inspect the report. The report, obviously, the signature is checked, and the content is also inspected. There is a database about well-known good components, which are considered to be trusted without known software vulnerabilities. And the verifier is comparing against these values. If the values are matching, that we are good. The result of the inspection decides whether the device is considered to be trusted or not trusted. Typical use case is the device onboarding. Before the device is access to a service, we want to make sure that we can send some secret data to the device. It won't be stolen. DICE is a layering concept. It defines how you can combine measurements from the multiple boot stages to create a chain. The main operation of the DICE is a key derivation, which is combining a compound device identifier, it's a CDI value, with a fresh measurement. This operation, this key derivation operation, is repeated as many times as the bootloaders are producing new measurements. From the CDIs, further keys, symmetric and asymmetric keys can be derived. Symmetric keys for data encryption, decryption, and asymmetric keys for signing certificates. The bootloaders also are producing the measurements, but also collecting some associated metadata about the boot images. These can be like identity of the signer or the software version or some kind of security counters. All these data is put together in the certificates, and actually the chain of the certificates are the actual attestation report which is sent to the verifier. DPE, so DICE can be implemented only in software, so it's a software implementation exists. DPE is an enhanced version of the DICE because you want to make sure that the report is correct. So in one hand, DPE is a set of hardware requirement, how to build isolated execution environment which can host DICE service and handle and store DICE secrets in a secure manner. On the other hand, it's a set of software requirements which is defining the interface and the behavior of such a DICE service. DPE is quite a loose specification. It leaves many details unspecified. It allows the users to create so-called DPE profiles. You can use your DPE service, I mean the basics, in a different way. The DPE profiles, for example, can define what data is actually sent to the service, how the certificates are encoded, whether is it X509 or CBOR-based certificates, and so on. Yep. Okay, so why DICE and DPE is important for ARM? So Google already use it. So Google chose the DICE attestation solution to implement the attestation service within the protected VMs under Android. They have a software-only implementation. It is open source in the Open DICE repository. You can find it in the Android 3. And yeah, they are actually use it in real products. So from Pixel 6 onwards, it's already in production. But the bootloaders of the Pixel 6 is obviously closed source, so there is no open source reference implementation available to look at it and learn from it. Attestation is not only the one use case which can be built on the top of a DICE chain. There is the sealing, unsealing use cases, which is about data encryption, decryption. Sealing means that you can bind data to a given version of a software because the encryption keys are derived from the certificate chain which was led to that software components. It has an impact that only the same version of the software component, or might be higher, a newer version of the software component, is able to decrypt the data which was previously encrypted by the software. So ARM, so both DICE and DPE, they are quite new standards. They are not yet widely adopted. Actually, DPE is still in progress. Right now, it's on public review, but it's not yet finalized. So further modification we can expect. ARM decided to make open source reference implementation of the DPE service just to showcase how can the DPE integrated with the firmware space and enable ARM partners to build upon that work. The ARM goal is to integrate our DPE solution in the long term with the Android pVMs works and to showcase how can a single certificate chain created which is covers from the immutable bootloader up to the pVMs user spaces, the entire software space. DPE provides extra security guarantees compared to a software-only DICE implementation. Okay, so you need a place where you can host your DPE service and you can run it because it must be an isolated execution environment which provide certain security properties. ARM has an IP which can fit to this purpose. It is so-called a runtime security engine. It's RSE. RSE, it's a secure enclave, but it's tightly integrated with the other cores on the same time, with the SCP and the application processor. There are communication channels between all of these three. RSE is access all the system memory, but on top of that, it has exclusive access to the one-time programmable memory and secure on-chip SRAM memory. RSE, in the OTP, you can provision in the factory the root secrets and certificates, and you can make sure that only RSE is access to that. RSE has an M-class based processor inside, and it is integrated with a crypto hardware accelerator. It has many security features like secure AI cache and encrypted memory. And as an extra, it is protected against side channel and physical attacks. So from functional point of view, RSE works as a root of the trust in the system. That is the first part of the system which is powered up after a reset, the immutable bootloader from the ROM code is executed by the RSE, and RSE is responsible to release reset the other cores and load the initial bootloaders. When the boot phase is finished, RSE can provide runtime services to the rest of the system, like the DPE. The firmware of the DPE is based on the Trusted Firmware M project. So DPE is executed on the secure side, run as a regular secure partition. We pick a previous version of the DPE specification, and we based our implementation on top of that. And we also picked up the OpenDICE and the Android profiles from Google. And all the details which was specified by the DPE profile, we followed the Android way to do things to make a compatible certificate chain and solution with what Google have now. We have a partial DPE support right now only. We try to keep it simple. So we focus on the Android use cases. First, we implemented all the commands which necessary to the attestation, and sealing will come in the near future. We implemented the derive context command. That's the main command in DPE, where you can report the measurements to DPE service, and you can instruct the DPE service how to shape your certificate chain and what to do with that. We also implemented the get certificate chain. I will come back to that later. Certify key is an extra, and for test purposes, we implemented this try context as well. We kept it simpler, which means that we have only a single plain text section, because we assume that the data between the DPE service and the DPE client won't leave the border of the trusted compute base. Therefore, no encryption is necessary on the data. If that assumption is not true, then of course the data is sensitive. I mean the hash values, the measurements are sensitive, then we should have apply encryption on top of that. It's worth mentioning. At the end, it's okay. It's worth mentioning that the DPE commands are CBOR encoded. Even with these commands, we haven't implemented all the parameters. If you check the DPE spec, you can see that the derive context command has 10 or 12 parameters. It's a really complex functionality. So some optional parameter was not implemented, and we added one custom argument to the derive context command because the DPE spec allowing to define custom commands or custom parameters. This is the certificate ID. We use that to simplify the way how you can group multiple software components into a single certificate. We did the development on the top of the Total Compute 2022 platform. It is the ARM reference implementation for the client space. The client space is about the mobile devices. Okay, this is a quite detailed figure. I know because I checked that you cannot really read the text in the boxes from the last rows. I hope if you check it online and download the presentation, you can read it better. But I try to explain. So at the bottom, there are the multiple boot stages of the RSE. There is the BL11, which is the immutable bootloader in the ROM code. BL2, which is an extension of the ROM code. It's running from the one-time programmable memory, and the BL2. On the right-hand side, there are the DPE services, runtime DPE services. Runtime services provided by the RSE. These are the crypto service and the DPE service. And in the middle, there are the other cores, SCP, which is the responsible for the power management, and the application core, the main core, which executes the main workload, Android and Linux. So there is an important bit here. the UDS. This is the unique device secret. The immutable bootloader and the unique device secret, these two together is the basis, the root of the trust of the DICE chain. Only the BR11 has access to the UDS. After the BR11 do the first CDI derivation, for that the measurements of the first mutable code and the UDS is as an input, then the UDS will be logged, and the rest of the system which runs any later stage, they cannot access the UDS. Okay, so before the DPE service is up and running, we have a few boot stages which are producing measurements. So obviously the DPE cannot consume them because it's just not running yet. So those measurements are just saved to the secure on-chip SRAM in a raw format. And when the DPE is up and running, I mean at the init phase, service is just consuming the measurements from the memory and do the same derivation as any later stages. The BL2 bootloader, it loads many things. It loads the runtime of the RSE, it loads the initial images of the SCP and the AP. And when all of these are done, then it gives the execution right of the AP. In the AP, we have the regular software stack from the TFA. We have the BL1, BL2, and the runtime, secure components, and usual non-secure components with the kernel and Android on the top of that. There are communication channels between the cores, SCP RSS and AP RSS. So all the architecture of the DPE is a kind of a server client architecture when you have a central service which is responsible to process and protect the DICE secrets, and all the bootloaders are clients of this service. Therefore, all bootloaders must be contains a library, a DPE library, which can encode and decode commands. It's a CBOR library and plus some extra. And also, it needs to contain a communication driver, which is dependent on your platform. When these are loading the components, chain loading each other, producing the measurements, a DPE command is encoded, sent to the DPE service. RSS is a single core and single thread running, so the AP is blocked until the DPE is processing the measurements. Until that point, AP is running in a busy loop. We did this integration on the Total Compute 2020 platform, and the code is already upstreamed to the TFM repository, the DPE code. The integration code with the AP is upstream to the TFA repository. And we also, it's not showed here, but there will be another side, we integrated U-boot as well. The U-boot patches is right now is out of 3, and all the code will be published this summer when the new Total Compute release will happen somewhere in July, August timeframe. I don't know exactly. Okay. DPE would have all the benefit if it would have been integrated the entire software stack from the bootloaders up to the pVMs. But this impacts the entire vertical software stack. It would require a huge work to do, and it would require a massive collaboration within the ecosystem to pull it off. So it cannot be done all at once, therefore, but it can be done in small iterative steps. So therefore, ARM came up with the idea of the hybrid solution. And the hybrid solution is about to mix the hardware-backed and the software-only solution from the Android to create a single certificate chain which is covering the entire software stack from the immutable bootloader to the user space. So with the hybrid solution, you can have a few benefits because first, the entire software stack is covered by the certificate chain. The UDS, which is part of the root of the trust, is only available by the BR11, the immutable bootloader. The rest of the software stack cannot really access to it. And you can have the possibility that gradually you can upgrade your software components to rely on the DPE instead of doing software-only DICE operation. But there is an obvious drawback that only half of the system is backed by a hardware solution, and the rest is still exposed to MAD software attacks. So it's not a final solution. It's not meant to be a final solution. It is just a stepping stone, beginning of the journey, let's say. Our goal was to showcase DPE to partners to create a reference implementation, and they can build upon it. It's worth mentioning that if there is your SoC is not has a secure enclave which can host a DICE secret, a DICE service, then you can still have benefit from the DICE attestation solutions. And I know that some people from Linaro is working on it to implement a software-only DICE in the TFA and trusted services space. Okay, this figure is more about how the hybrid solution works. At the bottom, there is the RSE, which hosts the DPE service. And at the top, you can see a simplified view of the software stack of the application processor in case of the Android protected VM use cases. So this is in the middle if the hypervisor, the host Linux, and here with green is the pVMs. So the early bootloaders, BR1 and BR2 on the AP, they are integrated with the DPE client library and the communication driver. When they are loading either the non-secure bootloader or the runtime of the ER3 or any component in the secure world, they do the measurements, encode that in a DPE command, send a derived context command to the DPE. DPE will store the measurements, do the DICE computation, and that means the CDI derivation, and that's all. The non-secure bootloader is loaded by APBR2. The non-secure bootloader is responsible to verify and load the root, the image which has the kernel and the init ramifesh, and another image which contains the pVM firmware. pVM firmware is the first piece of code which is executed in any protected VM in Android. Non-secure bootloader do the same, takes the measurements, send the derived context command. But the point is that before jumping to the kernel, there is another command, the get certificate chain, which is capable to request the DPE to provide me the accumulated measurements so far, put them into a certificate chain, and also the last level CDI values is returned by this command. Non-secure bootloader encode these to a DICE handover blob, and here it's append to the pVM firmware configuration blob. Because it is appended here, any pVM, when it is started, the pVM firmware can extend the already existing certificate chain, and in this way we can ensure that single chain will cover the entire software stack. Okay, my last slide. This is about the total compute platform. It shows exactly what is the certificate chain, what we are producing. The first 4 certificates on the left, these are produced by the DPE service on RSS. The blue line here is indicating the border between the hardware-backed and the software-only solution. And this is only some examples from the VMs. Of course, the VMs has as many certificates as they want. It is just an example here. The first certificate, this is the root certificate. It only covers 1 measurement, the first piece of mutable code in the system, but it has other information about the hardware, like the hardware identity, the security state of the device, and, for example, the state of the debug control unit. The rest of the certificates covering multiple certificates, we try to structure the certificates in the probable unit of the updatability of the system. By the way, the platform integrator is responsible to figure out how they want to represent the software components. So he can instruct the DPE service with the derived context command how to structure which components group together into a single certificate, what components to put in a different one. The platform does it work? Sorry. The platform certificate is about the RSS, mainly the RSS components, plus the initial bootloaders of the SCP and the APBR1. The AP firmware layer is the APBR1, 2, and the secure word, and so on. The hypervisor layer is about the non-secure bootloader, the kernel, the boot image, the pVM firmware. And at this point, we are extracting the certificate chain, passing it to the VMs, and these are produced by the Open DICE software-only implementation by Google. Yep, that's all. Thank you very much for your attention. And
could you go back to the slide with all the big diagram you had, which was hard to see? One more. This one, yeah. So to bind the software that you're about to load to the chain, so to say, you compute a hash or something that you use to derive the alias key or something like that. Is that hash computed on the AP or is it on the RSE? Okay. Okay, yeah. That's, I was curious because otherwise it could be a lot of information to send to the RSE. So.
Yeah, sorry. So we was taught about that we can add some extra custom command or custom parameters to the derived context to instruct the RSE to do the measurement as well. Because actually the weakest point when you are doing the measurements, if the measurement is unreliable, then actually you cannot really do anything with DPE to help. But if RSS know where the content was loaded and can do something against that, only RSE can access that system memory and locks everything else, then we can more reliable that the measurement was taken right.
Thanks.
Thank you. Two questions. One is a clarification regarding RSE BL12 that is mutable, but it is not, right?
Yeah, actually, because it's a one-time programmable memory. So,
okay,
yeah.
Cool. And the second question was, you have in the API exposed there is a certify key, right? And I was curious, how do you plan to use that, and how is that useful without a sign also that can use the actual certified key?
Historical reason. I mean, we picked up the 0.6 version of the DPE spec when we started the development. And since then, the spec has evolved. In that spec, there was no get certificate chain command. So the way how you can extract the certificate chain was the certify key. So that was our first implementation to rely on that. Then we realized, okay, they already added support to the get certificate chain, which fits our purpose more. So we moved on to that, but we kept the certify key because might in the future that will be useful for us. If, for example, DPE would be integrated with the rest of the software stack, I mean in the pVM user space, that time certify key can be useful.
Because, okay, yes, because the key pair is generated inside the pVM, and then you take the public key and say, certify me this thing.
Yeah, but that
and then you sign with the private that you hold.
Yeah, that time we probably need to add the sign command as well, because then all the functionality would be encapsulated within the DPE.
Okay. Okay.
Yeah, so work is still in progress. It's in experimental state.
Mhm.
Yeah,
Cool.
and we need to catch up with the spec updates for sure in the future.
Thank you.
So what is your plan for moving from the, what you call the hybrid solution to a hardware-only solution, which I suppose is the goal?
We did some initial investigation what kind of work should be done to reach that goal. We know that Google is working on some communication interface and transport protocol in the Android layer, which would allow us to integrate RSE with the rest of the software stack. But I don't know about any timeline information about that work. So right now we are basically waiting, showing what we have, and we are thinking with Google how can we go forward to implement the full solution. But actually, this is not, so this should be a community effort.
Thank you.
So speaking about Google, you mentioned OpenDice as well. Is this solution here also built on OpenDice? You have both the ceiling key and the CDI from all the way from the root.
Yes. So we use the OpenDice specification as our profile. Yeah. So we are extracting the ceiling and the attestation CDIs. The current implementation only the attestation CDI, but the ceiling CDI is also planned. Yeah, they use ceiling in the Android software stack in the secure storage solutions. So that would be needed.
Thanks.
Maybe a simple and mildly useful addition would be the get profile API implemented as well, so that you can tell the higher layer what exactly is available to them in terms of APIs and
Yeah,
it's a simple one, right?
it could I don't know. It could be tricky because so the OpenDice and the Android profile, they are not specified by the TCG, so there is no profile descriptions because the get profile need to provide a lot of information about how the profile behaves. So it's we can look into it.
I mean, one thing that it does is just lists what interfaces are available to the higher layers. And then it gives also a simple string that you can communicate to consumers so that they can know what, for example, a verifier. There's good information in the sense that the verifier is given all the context for verification, and if he knows what profile it needs to match against.
Yeah. In the hybrid solution, I believe it's not so important because U-boot is the client who extract the chain. But if it would be in a higher level software, or would it be sent for a remote verification, then I agree it would be useful to provide that info as well. And OpenDice and DPE spec, they were evolved in isolation. So we should map the OpenDice profile to the DPE spec to produce that information.
Sorry, not a question, but a clarification on what was asked before about the full solution. Correct me if I'm wrong, Tamas, but I believe ARM has no plans to independently drive or work alone on the full solution, right? So as Tamas was saying, it will require community effort. So if there is an interest to connect the hybrid solution with the higher layers, please do get in touch, everyone in the room, because that will need wide adoption for putting more effort in it. It's not something we I believe we are planning to do ourselves, right, Tamas?
No. Actually, we are not responsible. We are not responsible for those components where improvements needs to be taken. I mean, in the kernel, the hypervisor, they are owned by other entities. So yeah, thanks for the clarification.
Yeah, so I think it's fair to say that our work stops here, unless and until there is any other interest from anyone in the community.
To answer to that, well, to reply to that, if I have a way to remove the CDIs from the pVM firmware memory and put them somewhere in hardware, then I will use that, definitely. Because pVM firmware, or the dice chain of the pVM, of all pVMs actually, can get compromised if that CDI gets leaked. So
yeah, that's why I said this is not an ideal solution. So,
no,
yeah.
of course. So what I'm saying is, if I can move this out of memory into the RSE or whatever the DPE, then it will basically increase the security of the dice chain of those pVMs as a whole.
You need the CDIs. I mean, you need access to them in the hybrid solution. You need access to the CDIs in the pVM to be able to extend the chain.
Yes. So what I'm saying is, a hardware-only solution would be welcomed. That's what I'm saying.
Okay.
I'm the maintainer of pVM firmware.
Ah, okay.
Yeah.
Cool.
Sorry, the maintainer of?
The pVM firmware.
Thank you very much.